Welcome to Automated Flight Week 6, where we will continue with our second order equation and we will continue the math to look at stability in systems in a little more detail. Now here we have our mass spring damper system, and here we have written it in a more standardized form, and we can write the Laplace transform of our output variable x, which is this displacement of the mass, but in a generalized second order system it could be anything. We'll just choose it to be our output. We'll have our f of s over s squared plus 2 zeta omega n times s plus omega n squared. And we saw that the stability of this system depended on the zeros of the denominator. We can write those out. S1, S2 is equal to zeta omega n plus or minus omega n times the square root of zeta squared minus 1. And we see that really if these, well, there are a couple of conditions which we'll go into in a minute, but depending on the value of zeta, the behavior changes. So for example, if we have zeta larger than 1, the second condition is zeta equal to 1. We have, that's not a zeta between 1 and 0, and the final case, zeta is equal to 0. So if we distinguish these four cases for zeta, well, in the first case, we'll have two real zeros, which means we have an overdamped system. If zeta is equal to 1, then this term is equal to 0, and we only have one zero. We have a critically damped system, which means it's on the edge of being overdamped and being underdamped where it has oscillations. And here we have an underdamped system. So where it is 0, and then this root, this square root will become negative and we'll get complex roots. And if zeta is equal to 0, this root will become purely minus 1s, so we get complex roots, but because zeta is 0, they are purely imaginary, and we have an undamped system. Now, if we look for these four cases, 1, 2, 3, 4, and we plot our roots in the complex plane, we can see a couple of things happening. So the first one, if they are overdamped, and we're looking at a system where, for example, we have a mass spring damper system, we know that eventually it will, if we let time run to infinity, it will stabilize to a certain value, and we'll have poles on the negative real axis. So this is the real axis, and this is the imaginary axis. So they'll be somewhere on the real axis because there simply won't be an imaginary part. If it's critically damped, and I'll do that in a different color, so if it's critically damped, we'll have only one zero, and just we just write it anywhere on the negative real axis. If we have an underdamped system, we'll have roots which will have an imaginary, a real part and an imaginary part, which I will draw in red, and they will be here. Now, if we have two complex roots, they'll always be complex conjugates of each other, which means they'll be symmetrical around the real axis. Finally, if we have a completely undamped system, and I'll do that in green, we'll have poles that lie on the imaginary axis. Now, what does that say in terms of behavior? Well, an undamped system over time will simply show exponential behavior towards a certain limit. In blue, if we have a critically damped system, it will be a similar profile, but it will go to that value a bit faster and then continue on to that limit. If we have an underdamped system, we'll get oscillations, but they will die out. And if we have an undamped system, we'll have oscillations, but they will simply not die out. So these are the 4 behaviors we have for a system where if there is no damping, we'll just simply have an oscillating system. But if there's some form of damping, it will go for t goes to infinity to some limit. Now that doesn't have to be the case. We've drawn our poles mainly in the left half plane, except for these. But we can see that the green system is not stable. It will not reach a certain limit over time. But everything here is stable. We see that for everything in the left half plane, if the poles of the transfer function lie in the left half plane, it will be stable. If we have poles here, so we'll have a pair of complex poles, well, the behavior we'll see is that we'll have oscillations, but they will increase in amplitude. If we have, let's say, a pole on the positive real imaginary axis, it will just simply go towards infinity. So now we know what kind of the stability properties that we first derived for this system, how they tie in with the locations of the poles of the transfer function. Now, we haven't defined the transfer function here, but for this system, GS is the Laplace transform of the output over the input, and that here was 1 over s squared plus 2 zeta omega n s plus omega n squared. But this holds for any transfer function where it is a fraction of polynomials. So if we can write our g of s as some polynomial in the numerator and some polynomial in the denominator, and stability only depends on the zeros of q of s, which are called the poles of our transfer function. Now, it doesn't matter how many poles there are. Of course, the zeta is a property of a second order system, but we know that if we can write this as a polynomial, any pair of complex roots will form a second order polynomial with roots that will be either, well, somewhere in the complex plane with non-zero imaginary parts, and otherwise we'll just get single poles somewhere on the real axis. But everything still holds true. If there is any pole in the right hand side, the whole system will be unstable. It doesn't matter if there are 10 poles on the left hand side and 1 on the right hand side, that will force our system into instability. So when we look at transfer functions now, what we're really interested in is where do the poles of our transfer function lie. So for stability, location of the poles of our transfer function. If they are in all in the left half plane, so on the left side of the imaginary axis, we have stability. And if there are any in the right-hand plane, we will have an unstable system. And keep in mind is that we are given a plant. It is not guaranteed that we can design a system where all the poles are in the left half plane. Sometimes we just have a system that is unstable and we have to find a way of dealing with it, and that is what we do with a controller. We take a controller and typically have some kind of reference point which we will, let's say we have our output y here and our g of s here, our plant, our system. We take the output, feed it back, and subtract it from the reference where we get our error. That will go into some controller, and the controller together with the plant, well, the aim is to get our poles into the left hand, the left half plane, so that we at least have a stable system. But it is not simply as easy as getting it into the left half plane, because we might have all kinds of other requirements. And I'd like to go into some of these now. But most notably, I'd like to start with an underdamped system where we have decaying oscillations, which is, for example, for these 2 points, we'll have oscillations, but they'll decay. Now, if we look at the solutions of the denominator, so we had S1, 2 were equal to zeta omega n plus or minus omega n times the square root of zeta squared minus 1, and we have that zeta is between 1 and 0, so this is our underdamped case, which has behavior where if we apply a set point, it will show some oscillation around some limit, but the oscillations damp out. What we know is that we have complex poles of the form zeta omega n plus or minus j times omega n times the square root of 1 minus zeta squared. So we've factored out a minus 1, that ended up being our j here, and then you can write this, and then we know that this is now a positive number. Now, if we write this in the complex plane, something interesting happens. So let's say our poles are in these locations. Well, we know that the y component, although this is the real axis and this is the imaginary axis, but this distance here is omega n times the square root of 1 minus zeta squared. And the distance here is zeta times omega n. And we can draw a vector to this point, as we do sometimes with complex numbers. Now, if we take this angle zeta and the length of this vector, well, we can calculate the length of this vector because it's the square root of this term squared plus this term squared. Well, let's write it out. The length is zeta squared omega n squared plus omega n squared times the square root of 1 minus zeta squared, and we take the square root of this term. But if we calculate this, this term squared is nothing but 1 minus zeta squared, and if we add these two together, we see that the length of this vector is the square root of omega n squared is equal to omega n, because omega n is a positive number. So we know that the length of this vector is omega n. I will just erase this because we've just derived this. But something else interesting happens. If I look at this theta, this angle theta, I know that the cosine of theta is theta omega n divided by omega n. So zeta omega n over omega n, and we end up with zeta. So any set of poles, and I'll write this in this figure, any set of poles that is on the line with angle theta will have the same damping ratio. So if we have two systems here where the poles are on a line with angle zeta, and I have a second system with poles on the same lines, I know these two systems have the same damping ratio. What is the difference? Well, there's a difference because the distance from the origin here and here is different, but that characterizes the natural frequency. So this system will have the same damping ratio, but a higher natural frequency. And this ties in with something we want to do beyond having our system just be stable. We might want to have a system with a certain set of properties. We might want to have a limit or a lower bound for the natural frequency. We might want to be in a certain range for the damping ratio, because if we have a damping ratio which is too low, we might have a very slow system, and if it's too high, we might get oscillation. So if we have a system where we say, well, I want this system to be within set limits of a damping ratio so its behavior is nice, I might choose to set an upper bound zeta upper and a lower bound zeta lower, and say, well, once I've built my controller, I don't want the poles to just be in the left half plane. I also want them to have a certain damping ratio. And the same goes for the natural frequency. I might want to have a lower bound on the natural frequency, and I might also want to have an upper bound on the natural frequency, because I don't want it to oscillate too quickly, but I also don't want to have oscillations that might be so slow that they cause excessive amplitude or something like that. So instead of just wanting them in the left half plane, I want my zeros, in any case if I have complex zeros, to be in a certain region. And of course they can end up on the real axis as well. They'll be stable there as well, but anything with oscillations I might want in a certain region. Now, in the next video, we'll see that, of course, we would like, if we look at our transient response, our response, the initial response to a step input, well, we'd like to have it be completely perfect. So ideally, if we have a change where our system will eventually settle, we don't want excessive oscillations, we don't want a very slow system. Now ideally we'd go up and settle very quickly without any oscillations, without any overshoot. But in the next video we'll see if we look at the transient response, we cannot have it all. We cannot have a very fast rise time and a very small overshoot and a very short settling time, all with the same, all be optimal at the same time. But so, just to recap this part, is we've looked at the second order system, we've looked at the properties of the damping ratio, and we saw that for different values of the damping ratio, we got our poles and zeros in different areas of the complex plane. We saw that if we tie that into stability in general, we look at the poles of our transfer function, and as long as they're in the left half plane, we'll have a stable system. And if anything ends up in the right half plane, we'll have an unstable system, which we'll have to remedy with a controller. But we also see is that we don't always want them to be just in the left half plane, and depending on our design criteria, we might want them in a specific region in the complex plane. In any case, the ones which have an imaginary component. So we'll continue with this in the next video.